that look okay? So, it's recording?
Yeah.
Okay. All right, so this is the last lecture. Remember, all the quizzes, the online quizzes, are to be done by noon on the 11th of May, which is the 11th of May, which is a Thursday. Also, I have a special announcement. On the 11th of May, a biophysicist who's won the Nobel Prize in, I guess, medicine and chemistry and medicine, or medicine and physiology. Anyway, one of the Nobel Prizes. And he's talking here in this room at 3:30 on the 11th. So quizzes are due by noon. If you want to learn something, come by at 3:30 in this room, and there's a public lecture by, I think his name is Morner, or something close to that. And I imagine he'll give a lecture that will be interesting, and you'll be able, I think, to learn something from it. He also is said to do some sort of a demonstration here, and so I think that will be nice also. I put I put 12 new web pages on the class website, but unfortunately, the guy who is responsible for the demos and the setup did not show up today, and we're having trouble getting the computer going. In any event, I'm sure that any of you who have access to the internet now can just go to the class website, and you'll go down and you'll find there are 3 or 4 that are just chapters from a book that I'm sort of writing, although I don't promise to finish this one at all because it's on biophysics. But I started writing it, and there are 3 or 4 chapters that I put online. And then I put 9 panels from an excellent book called Molecular Biology of the Cell. So if any of you wants to go into, or if any of you want to go into biology, medicine, biophysics, any of the life sciences, even for that matter chemistry, I would say it would not hurt at all to look at the book Molecular Biology of the Cell. It's one of the best books for science students ever written, and in fact it's quite a useful book for professional biochemists, molecular biologists, biophysicists, and so forth. The writing is really good for a change. There are other books that are just dreadful in molecular biology and biochemistry, absolutely appalling writing. People who use negatives, use sentences with 2 or 3 knots in them, who use the passive voice all the time, use complicated, confusing verbs like comprise, and pride themselves on foreign Latin and Greek plurals. Anyway, terrible books, but Molecular Biology of the Cell is a marvelous book. And one of the curious things, I had the good fortune to chat with one of the authors, and he told me that the 5 or 6 authors trust each other so much that they follow a wiki book procedure. Namely, any of them can edit anything in the text. They all have the text, and either a Word file or a LaTeX file, probably Word, unfortunately, but anyway. And any of them can edit the writing of any of the others. And so this cross-fertilization of language has made it into a book that's a pleasure to read. And that's especially true of the first 5 or 6 chapters, which of course are also the most important ones because they introduce all the basic concepts of atoms, molecules, genes, evolution, basic concepts of biology and molecular biology, organic chemistry. So, what is, all right, I guess there has been well, this is really a pity because, as I said, I spent a reasonable amount of time getting, oh, good, we've got an expert. Okay, we have various demos here, and all right, let me do this demo because it's kind of a gee whiz demo. I think I already turned it on, but you might be amused just to see it again. I think this is called Jacob's Ladder, and it may have appeared in a movie, but I don't know. At any rate, what we've got is high voltage across these 2 copper, basically very thick copper wires or copper cylinders probably. And what happens is the voltage jumps across at the bottom here, ionizing the atoms of air. The air then becomes very hot. Because it's hot, it rises. And once it escapes, then the 2 copper cylinders are no longer at the same potential, and then at the bottom, where they're closest together, the voltage is highest because electric field is voltage divided by distance, and so the very high electric field at the bottom ionizes the air, and that starts another one going up. Great. Also be nice. Oh, you've got actually something.
What's the noise we're hearing?
I'm sorry, what?
What's the noise?
I honestly don't know. It might be the noise of ionization, but my suspicion is it might just be a noisy transformer.
Well, it kind of like pops whenever it goes to the top.
Does it stop when it gets to the top?
It's like,
Well, clearly when it gets to the top, the ionization process stops, and the electric current going across stops, so that creates a sound. But the constant hum, I think, is probably the hum of the transformer. That's a guess. I mean, I don't know. I didn't, by any means, build the thing. Yeah.
So if the wires kept getting farther apart,
Yeah.
if this went up much further, would there come a point where the electrons would no longer be jumping across?
Okay, good question. In fact, let me toss you a candy, although now you're getting 2 of them, and I'm very short. I went to Costco twice, and each time I forgot to buy more candy. It's, I don't know, it's, every semester ends in a train wreck. That's basically my feeling of my experience from teaching. So, to your question, the electric field is the potential difference, which, since these are copper and nearly perfect conductors, is the same all the way up to the top. So the electric field is less. If you extended it and separated them more and more, eventually the electric field would get low enough so that you could no longer ionize the atoms. And what's really happening is that electrons are jumping from one copper pole to atoms in the air, which then are accelerated in the electric field across to the other, I guess, positively charged copper cylinder. And as that ionized molecule goes across and goes faster and faster, it disturbs other molecules, which then lose or gain electrons and go forward or backward according to whether they're negatively or positively charged. So that's basically what's happening, and if it gets too far apart, then nothing happens. It turns out, let's see, well, I don't know. I thought these guys were going to solve the problem. Anyway, it turns out that, especially in New Mexico where it's so dry, because the other thing is that it's warm in New Mexico, so we don't heat the houses that much in the summer. I grew up in New York City where winters are cold, especially when I was young. Before global warming, they were really cold. Anyway, in New York at that time, we would have steam heat in apartment houses. And of course, the steam heat meant iron pipes which carried steamy water or just steam. And sometimes, I remember as a kid, I'd walk across the rug and put my hand somewhere near the radiator, which was, of course, iron, and a spark would jump out from my hand to the radiator. So you can charge yourself to thousands of volts with static electricity, but, and that's much like when I did those demos, remember rubbing cat's fur or something else against plastic or rubber to ionize one, build up the charge on one. So you build up a charge walking across a rug floor, but the amount of charge that you have is not great. And so, although the voltage is high, you discharge it when the spark jumps across. Now, sometimes you might even be in a circumstance where you have to, you know you're going to be charged up, and you have to turn on a water faucet. And you don't want to get a shock. So what you should do is grab a key, touch the faucet with the key. Then the current going out of your body flows through a couple of square centimeters of skin on the base of the key, and the spark will jump out the tip. So what hurts is the current density, not the actual current. Although for large currents, obviously, that would hurt too. But for just getting discharged, just trying to discharge yourself, just doing that, bingo, the spark jumps across and it doesn't hurt. Okay, well, I'm sorry I don't have anything to show you with the on the class web page. Let me turn out the lights and do one of the demos that I've done before. In fact, I'd like to turn off those stupid blue lights now. What we have here is a this is a small laser. In fact, I can hold this up and sort of show it to you. This is a small laser. In fact, it's a diode laser. And this is a variable slit. It's an open slit that I can close. And so you can see what happens as I close it. You see the spot is bright, and well, I can tell it's a circle. who are sitting near the front may be able to, if they have really good vision, tell that it's a circle. And now, notice that the measurement of the momentum, or the position of the photon in this direction, as it goes through the slit here, I would say that that thing is open by about 2 millimeters. And so this is a very crude measurement of the horizontal position of the photon. But now as I screw this thing down, I'm down to about 1 millimeter. But now as I get it, and this is the one that's happening, it's down here. Now as I get it, I would say it's I don't know, half a millimeter. As I squeeze it down a lot less than that, I'm starting to spread the beam out. It goes out as far as there are actually some photons that go really far out. So it's about 60 centimeters now. And even more now. So this is a very nice, this is nicer than the demo I did previously, although it'd be nicer if that laser was stronger. In any event, you see the thing, the central maximum is really spread out. And that's because we're measuring where the photon is this is the x direction. We're measuring the x position really accurately. That means that the x momentum is very uncertain. And what that's saying is that the wave function that tells the photon where to go is really spread out in momentum space, and consequently the photons are going like this rather than straight ahead. And boy, that's even better. Now this is almost, the central maximum is almost a foot. I don't know if you guys in the bleacher seats back there, well now it's very wide, but there are hardly any photons getting through at this point. Okay, so this is an example of Heisenberg's uncertainty principle, which is that the error in position times the error in momentum in the x direction is greater than more or less Planck's constant over 4 pi. And Planck's constant is, of course, very small. I don't memorize it. In fact, in most calculations, it said equal to 1. If the computer system were operating, I'd be able to Google it, and you could get I could quote the value to you. Actually, you're sitting there right in the front row with a copy of Weinberg's book. If you flip back in Weinberg's book, he must say what H or H bar is at some point.
The math part?
What?
To the mathematical part?
Probably, but I don't know. I was reading that in the first few weeks of this course, and I've read the book a couple of times. It's one of the best books written about science for the general public, although when Nobel laureates address the general public, they sometimes have a funny idea of who the general public is.
What is it called?
They mean basically people like you.
I know that's something bar.
Anyway, it doesn't matter. It's a very small number. The units are energy times time. Now, I keep mentioning this wave function that tells the electrons where to go, or tells the photons where to go. One thing I thought of as I was walking over here today was say something about what the probability distribution is for, say, an electron around the proton of a hydrogen atom, and I think the 2 shouldn't be there. I think that's just in the wave function, whereas this is the square of the wave function. And so this is psi. This is the absolute value squared of psi of R. dV is the volume element. And this thing goes as e to the minus r. This A0 is the Bohr radius. Bohr produced the first quantitative model of the atom back in 1912, which is now 105 years ago. This is called the Bohr radius. And it's of the order of 0.5 angstroms, actually. So it's really, since we're using MKS units, it's about a 20th of a nanometer. It's half an angstrom, and an angstrom is 10. So this is 1 over 20 times 10 to the minus 9 meters, or 5 times 10 to the minus 8 meters. And I have that right. Oh, I'm sorry, this is a 10. Right. Okay, so that's the size of a hydrogen atom, and this says that if the proton is here, the electrons, the probability of the electron being somewhere is highest right at the proton, but it's spread out and falls off exponentially, and that means that for R less than A0, falls off slowly. As R gets bigger than A0, falls off fast. And so it looks something like that. P versus R. We have another demo here, which is also quite nice, but I think I need to turn the lights out again. This illustrates photons. They're coming out of this laser, and what we have here are 2 polarizers. And here, what's happening is that this polarizer here is letting through basically half of the photons. And this polarizer is also letting through half of the polarizers. In fact, it lets through the ones that are polarized the same way this one is polarized. Yes?
What are polarizers?
Give me that again now. What?
What are polarizers?
What are polarizers?
Yeah.
Well, that's...
I mean, like photons, I get photons move in different directions, but...
All right, these are linear, as far as I know, these are linear polarizers. And a linear polarizer, again, as far as I know, is basically a substance that allows electric fields in one direction to go through, but prevents the ones that are in the other direction. And we saw this, an example of this in the microwave demo. And remember, the difference between microwaves and photons is just that the microwaves have a much lower energy and longer wavelength. And so what basically, you see, the photons, as they go through, these photons that are coming out of here are coherent. And that means that that means several things. It's that they're all in phase, they're all moving with the same energy, they're moving in the same direction, and they basically, although they're photons, they collectively form a classical electromagnetic wave of the kind that Maxwell described 150 years ago. And so those photons then, let us say that they're describing an electric field that's going like this. All right, if the electric field is going like this, and it goes through a polarizer that is made up of, say, tiny copper wires that perfectly conduct, and they're also in this direction, well, what happens? The electric field of the photons is absorbed by the electrons in the wire because those electrons start going up and down. So the energy of the wave is transferred into the energy of the electrons moving in the wire. And the result is that fewer photons get through.
So even though both of those are the same direction, less photons are getting through than if there was no polarizers?
Right. Let me flip this light on then just for a second. If you have an electric field like this and it's passing through a screen that has, so the electric field of the photons, of the collective coherent state of the photons is vertical, and the wires are also vertical, then this electric field starts moving the electrons in the wire. And consequently, the energy of the wave is absorbed. And in effect, the photons are absorbed. So few photons get through. On the other hand, if the electric field is this way, and the wires are this way, then the photons just go right through the screen between the wires. So, roughly speaking, that's how it works. Of course, to actually do this was a feat of technology back in, I guess, the 1940s or 50s. It was Edwin Land who figured out how to make cheap polarizers. He first made sunglasses, and then he made a camera. Whether the camera has anything to do with polarized light, I don't know. But he made sunglasses that were a commercial success. And his camera company was also a commercial success. It was one of the glamour stocks of the 1950s and 60s. He then gave much of his fortune to an institute called the Broad Institute in Cambridge, Massachusetts, which is doing biophysics, biology, molecular biology, medicine. It's doing medical research that will lead to a better understanding of living things and also major advances in medicine. In fact, the Broad Institute is one of the institutes that has that developed the gene editing technique that has been developed over the last 5 or 10 years. And I've forgotten what the buzzword is. Does anybody remember what the buzzword is for that gene editing technique? No, all right. Anyway.
It's not stem cell research at all, is it?
What?
Has nothing to do with stem cells, right? Or is that a different?
No, it's not particular. It has to do with every kind of cell.
Okay.
But, all right, anyway, to get back to the polarizers. This polarizer lets through photons that I think are polarized in the direction of this, since their electric field is parallel to this white wire, this one likewise And now the funny thing is, if we put in another first of all, let me do this. Let me now turn this polarizer so that it is perpendicular. So now essentially nothing is going through, because the only photons that can go through are the ones that are perpendicular to both sets of wires, and basically you can't be perpendicular to two things that are perpendicular, and so nobody gets through. The amusing thing though is that if you have another polarizer and you put it here in the beam, something gets through, you see. See, now something gets through, and if I turn it a certain way, a lot gets through. In fact, I can arrange it so that half of them get through. The way, yeah, that's actually, I don't know if I was actually getting half of them through, but half of them come through this one. And if I then turn this so that it's basically like that, then maybe a quarter or so are getting through. And one way of thinking about it, in fact, the way people think about it, the way it's formulated in quantum theory, is that the photons coming out here are in two possible states, because they're unpolarized. This one throws them all into one quantum state, but the ones that go through this filter, this polarizer, have to be in another quantum state, but this quantum state is not orthogonal to this state, and it's also not orthogonal to that state. So when the photons go through this state, they are now, in fact, maybe vertical is probably the easiest way to do this. When they're going through this one, they now are no longer prohibited from going through this one. And so it's a puzzling thing. In general, these polarized filters cut out half the photons. But in this case, they take the photons that are in a particular state, throw them into another state, and when they're in that other state, some of them can get through here. So the idea is that in quantum mechanics you have a space state, and the space state is two-dimensional for polarization. And the reason it's polarization is two-dimensional is that massless particles can be, what we're really talking about here is the angular momentum of the photons. The angular momentum of the photons is h bar. Planck's constant divided by 2 pi. And the angular momentum of the individual photon can be either parallel or anti-parallel to its motion. So those are two different states that are orthogonal to each other. That creates a two-dimensional space. And what happens here is that, and in fact you can think of the states as unit vectors from the origin pointing in some direction in this two-dimensional space. So they can point along the x-axis or the y-axis. And I guess I should turn on some of the lights now. So these photons, you can think of them as making a two-dimensional space. Some of them are this way, some of them are that way. Now, if you just have the two polarizers, one lets through photons that are in this state, the other one lets through photons in this state, but no photon can be in both states. What happens, though, is if you use the middle polarizer, say the first photons come out with the first polarizer like this, the next polarizer is like that, and says that the photons are this way. So some of the ones that are going this way can be going this way. And some of the ones this way can be going that way. And so even though polarizers absorb photons, and you'd think that by sticking in the middle polarizer, you would be lowering the beam on the screen, which was already zero. In fact, you increase it.
So the photons are going in all directions then?
No, the photons, there are two things involved here. There's the photon momentum, they're always going forward. What you do have, though, is the angular momentum of the photon. And it can be either parallel or anti-parallel direction of motion.
And with that laser, it's parallel? With that laser, what is it? Is it parallel with that laser? Or is it...
The lasers puts out things that are unpolarized.
So parallel, right? Or anti-parallel?
Well, it's that they're not in what we call a pure state. In other words, this laser is throwing out photons, all of the same energy and momentum, but some of the angular momentum is this way and some of it is that way. Although actually they're going this way.
But it looks the same when they're...
Same momentum,
Yeah.
same color.
Okay. It's just a difference in the electric field?
Well, all right. Now you're pushing me to really explain the thing in terms of mathematical formulas. What happens is, if you take a linear combination, in fact, a complex linear combination of the two circularly polarized states, you get a linearly polarized state. And that one has the electric field going in one direction or the other. All right, I think I've pushed that far enough. Yeah. All right, what we've got here is, I'll turn the lights out again. This is a demo I've done before, and it's one of my favorite demos, and I asked for the small Tesla coil, and because I wanted to fire up the Tesla coil and move it near these cylinders of gas. What I've got here are some, these are some transmission gratings. So here, why don't you take one and pass them on, or take two if you want, because, you know, one might not work well. And so what I'm going to do is I'm going to start here with xenon. So this is a rare gas. Well, we've got a problem, Houston. I can't get this thing to work. Let me turn the lights back on. So this lecture on the internet is going to be a real advertisement for how screwed up.
Hey,
Here we go.
There it is.
Now, why did that happen? All right. Okay, so let me turn this off. The lights, I mean. And I've got a little bit of slack here so I can move it closer to you. Okay, this one is krypton. Do you have the camera aimed at more or less the demo here? Of course, what you see with the naked eye is you just see it as white. But if you hold up one of these things like this, then you can see that this transmission grating will take, in other words, there are photons coming out of here of many different frequencies corresponding to the different transitions. And in fact, to be less mysterious, I see mainly 3 strong lines: green, yellow, green, yellow, and red. And what's happening then is that the red line is bent more, and the blue-green line least, and the yellow line more. So they're separated by this transmission grating, and and you can see these different transitions. So let me turn that one off. That was krypton. One of the prettiest ones, of course, is hydrogen, and that's why some of the photographs of planetary nebula, which are gas ejected by previous exploding stars, are so pretty, because here what we've got is, I guess, well, several strong lines. The strongest ones are a sort of blue-green and a red, and that makes this lovely rose color that's characteristic of hydrogen. So when these stars explode, they blow out a lot of hydrogen gas into the atmosphere, and by the way, the way to, let's see, let me get as far away as the students are so I can see what the correct way to do it. What you want to do is you want to hold the transparency, the transmission grating, so that your arm that's holding it subtends an angle of about 15 degrees with the ray that goes directly from your shoulder to the bright red tube. Then you get to see then as you move the transmission grating, you'll be able to see the different lines. So that's the way to do it.
It seems like that one has like areas that don't have any.
Yeah, that's right. And the reason is that hydrogen, this is hydrogen, molecular hydrogen, of course, rather than atomic, because when you have atoms of hydrogen, they attract each other and they form H2. And that's actually a covalent bond. And it's about 5 electron volts binding the 2 atoms together. This is H2, but still H2 is a very simple system. It only has 2 electrons. So the number of transitions is lower. The more electrons in general that you have in your molecule, the more complicated is the transmission spectrum. And that, of course, is the origin of the greenhouse effect. Namely, that with carbon dioxide, you've got an atom of carbon, 2 atoms of oxygen, and so you have all these outer electrons that can undergo all sorts of crazy transitions. So you can absorb and emit in many, many different frequencies. Methane is even worse because it's 1 carbon, then 4 hydrogens. So you have all sorts of... Let me try xenon again. I think it's that I didn't turn this thing the right way when I... No. Ah, yeah, it is working. Okay, so this is xenon. Now, xenon's a rare gas, and so in the outer part of xenon, you have
It's really faint.
a lot of... Boy, I'm not seeing anything with this.
It's really faint. It's there.
Yeah, it's not
It's
only
faint and
faint, but
blurry.
it's really spread out. It's in, and that I think is it's because xenon is quite heavy, so it has lots of electrons in these outer orbits. And xenon, like every rare gas, has enough electrons to fill all of the quantum states in each level. And so what you have is you have a radial quantum states, and then you have orbital quantum states, and then spin quantum states. So you have enough to fill all of the orbital and spin in a given radial level. All right. So we've done hydrogen. Let me switch to krypton. Krypton I think is, yeah, krypton is quite sharp. I could flip the periodic table here. I don't remember, is krypton heavier or lighter than xenon? I don't actually remember. Okay, let's go to water. Now, water is going to have 2 hydrogen atoms and 1 oxygen. And so because of the hydrogen, you see some red. And there you can see basically 4 strong lines, but red is the strongest, and sort of blue-green is next strongest. So once again, if you're a student, you need to have something like 10 or 20 degrees between your arm and the, and you can go either way. You can go to the right or the left. So that's water vapor. Water vapor is also a greenhouse gas. Now here's carbon dioxide. And you see that's white. And boy, oh boy, look at that. There you see just a gazillion strong lines, all sorts of violet, green, a lot of orange, not much red. So that's one reason why carbon dioxide is a potent greenhouse gas. And the trouble is, it goes up in the atmosphere and it stays there for hundreds of years. This is Mercury. And it's kind of ugly to look at, I think. It's, we've got 3 strong lines, yellow, blue, yellow, green, and purple. Mercury is also poisonous, like most heavy metals. Here is argon, and argon is another rare gas. Oh, very faint. And of course, the reason it's very faint is probably that the strong lines are in the ultraviolet or infrared, where our eyes are not sensitive. Then is neon, another rare gas, and neon has very strong lights, and this is why. And these lines are mostly in the red, the orange, and the yellow, and it's very bright. Back in the 40s and 50s and 60s, many establishments that operated at night, especially bars, in other words, public houses if you're British, would have signs saying open or bar or beer or something, or advertisements for Budweiser, Schlitz, or some other beer. And they'd use neon gas because the light is so strong. All right, finally, helium. This is one of the 2 elements that was produced in the Big Bang in a big way. And you see here with helium, because you've got 2 electrons, you've got various lines here, and purple, green, yellow, red. So I guess there are 4 strong lines in helium. So helium is basically two electrons around a nucleus that's very tightly packed. In fact, helium atom is a perfect Fermi system. It has the ground state of the nucleus is one proton spin up, one spin down, one neutron spin up, one spin down, all in the same spatial state, so as compact as possible. And then the gluons inside each of the protons and neutrons can pull these protons and neutrons together into the same quantum spatial state. And then the spins are all aligned in appropriate opposite directions. And then there are two electrons flying around it in the nest state with opposite spins. Okay, let me try to see what we have here. We've got one more demo. And actually, I asked for another demo that did not. I asked for two other demos that didn't show up. One was the spark chamber demo, which hasn't shown, which they claim they can't get to work. Now, yeah, I'm sorry about that. I don't know why somebody set it up like this. I guess what we're supposed to see here is that just a slab of glass polarizes light to some extent, and so how am I going to do this? I think the way to set it up is this way. So now, we've got a polarizer here, and as I rotate it, you see the spot is pretty bright this way, but if I rotate that by 90 degrees, then it gets quite a bit darker. Well, that was only 45 degrees or so, but it gets quite a bit darker. And that's because unpolarized light hitting glass, metal, and many other surfaces is naturally polarized. And that was the trick that, that was the experimental fact, of course, was known probably in the 19th century, but in the middle of the 20th century, Edwin Land, when he figured out how to make cheap polarized sheets of plastic, realized that this could be a commercial success because sunlight would bounce off water and be polarized, and then if he gave people sunglasses that blocked the light that had the polarization that would come from the characteristic of light bouncing off water or off the surface of cars. So you're in traffic and the sunlight and the sun is bouncing off the hoods of the cars in front of you, comes through the windshield, and it's polarized, but if you don't have sunglasses on, then it can still be blindingly brilliant. And so he sold these polarized sunglasses, which were a real boon. One could make the front windshield of cars polarized, but then at night they would block out half the photons, and that would make night driving more dangerous. So I guess that's why it didn't happen. So now if I switch to the other kind of other polarization, you see it gets quite bright again. And then once again, dark. Okay, so that's that demo. So, as I said, I put these nice things having to do with, organic chemistry and molecular biology on the class website, but I can get that working, and so I'm going to have to do it from memory, which my memory is certainly not perfect. So I'll erase this Heisenberg uncertainty principle and just remind you of some of the simplest compounds. This is methane, although even simpler is just hydrogen. Molecular hydrogen is two hydrogen atoms, one covalent bond between them, and what that really means is that you have one proton here, one proton there, and if you look at the electric field produced by these, what you see is that the field, the minimum of the field is in sort of this region. It's, or minimum in an algebraic sense. In other words, the electric field is strongest near the two protons, but also it's pretty strong, or the potential, I should say, is strongest at the two protons, but it's also pretty strong in the in between them, and it's weaker out here and out here. So the electrons tend to go here. But if you have a lot of negative electrons clustering here, they attract the two protons, and so that's the nature of a covalent bond. If you put a lot of these guys together, you can make a big string of carbons like this, and when you make such a long string, you've got what is called a hydrocarbon. And these hydrocarbons are basically of the form CH2, n units of CH2 plus an H at one end and an extra H at the other end, if it's linear. These things can also branch. The funny thing is, I don't recall they're forming rings. Although there is another ring compound, which is, of course, a famous compound called benzene. And there, what you've got is you've got a hydrogen off here. But now you see the carbons, which can naturally exchange 4 electrons, are only exchanging 3s. These are 3. These are carbon atoms. And so what actually happens is the electrons exchange, the carbon atoms exchange electrons with each other. And so they can form a double bond here, a double bond there, and a double bond there. Now, every carbon has, you can see 4 bonds. 1, 2, 3, 4, 1, 2, 3, 4. So this is benzene. Now, it turns out that an actual benzene molecule is quantum mechanically is a linear combination of 2 states, one being that, and the other one being like that. I'll leave out the hydrogens. So in other words, this carbon sometimes is exchanging its electrons with this other carbon, sometimes with that other carbon. Okay, now, there are also sugars, and sugars are carbohydrates. So these are hydrocarbons. And these things often form pentagons or hexagons, and when the ring is basically 5 units, 5 carbons, 5 oxygen, and 10 hydrogens, and I don't quite remember how it goes here. I mean, it might be like this, but that's why I wanted to show you these. If you go to the class website, you can see what it actually looks like. But ribose might have an oxygen here, a hydrogen there, and so what do I have? 1, 2, 3, 4. Maybe the carbons are at all 5 of these. And then you have an oxygen, a hydrogen. You certainly will have an extra hydrogen here. I think these are all single bonds. Oh, we've got 5 oxygens. So there could well be. All right, I don't remember the exact chemical structure, but it's basically a pentagon if it's 5 of these guys. Could be linear, but it also, that's the thing about sugars. They can form so many various structures. Anyway, this is called ribose. There are other sugars called glucose and sucrose and so forth. Now, a very important other class of organic molecules are the amino acids. And maybe I'll write them. Well, this is a totally blank sheet place, so I'll write some of them here. So amino acid is a nitrogen, a carbon, and then another carbon. And this nitrogen, if it's simply an amino acid, it will have 2 hydrogens. This is what it would look like in empty space. This carbon will have an oxygen, and in fact 2 oxygens. And this will have a hydrogen, and, well, actually it could have, if it's an amino acid, it could have, I'll just write this as R. R can take 20 values. In amino acids that are important in living systems, or most important in living systems, there are 20 different R's. One is just a hydrogen, so the very simplest is just a hydrogen. But instead of hydrogen, it could be CH3. Or all sorts of other things. So there are 20 altogether there. And then there's another hydrogen coming off that. And now what we've got is 2 bonds there, and one of these oxygens will also have a hydrogen. So everybody has the right number, all the atoms have the right number of bonds there. This is called an amino acid. And the reason it's called an acid is that if you put the thing in water, then this hydrogen atom can lose its proton. The proton can go wandering off, and then what you have is a negative charge here. You have an extra electron, and that extra electron is shared between these 2 oxygens. And because of the symmetry, this double bond flips back and forth. And this proton that was liberated, sometimes, again, if this is in water, this proton will go around and find itself here, because this is a negatively charged region. And the proton will stick there. So, In water, what you have is N with 3 hydrogens, one of them being just a proton, carbon to some one of 20 side groups, a hydrogen, carbon, oxygen, oxygen, and a minus sign, an extra electron. And in fact, I would write this as P for proton. So this thing is positively charged here, negatively charged there. So that's what an amino acid looks like in water. Okay, well, amino acids can bind together, forming peptide bonds between this end of one amino acid and this end of the next amino acid. And so they form chains, and at each step in the chain you have 20 possible amino acids. So this gives rise to an enormous number of proteins. For example, a common protein might have 200 amino acids. Each amino acid, there are 20 choices. So that means that the number of possible 20 amino acid proteins is 200 raised to the power, no, 20 raised to the power of 200. Okay. So for a 2 amino acid, you have 20 times 20, which is 400. On the other hand, yeah, all right, 20 times 20, and the order does matter, so that's 400 possible amino acids. When you come to 200 amino acids, it's just a number that's absurdly large, larger than a Google. And so obviously there has to be in living systems information to tell the cell how to make what proteins to make. And that information is stored in DNA. And DNA is basically a sugar phosphate backbone, and attached to each sugar is what's called a nucleotide. Or another way of saying it is it's just a chain of nucleotides, because nucleotides contain a sugar and a phosphate. But the nucleotides link up to each other, forming a sugar phosphate backbone, and then the things that distinguish one nucleotide from another just hang off the sugar part. And that would be then a single strand of either DNA or RNA, and the D or the DNA means that one of the extra hydrogens on the ribose is not there. That's DNA. In RNA, that hydrogen is there, so you have the full sugar ribose. There are basically, in DNA, there are 4 possible, they're called, well, 4 possible ring structures, which are called either purines or pyrimidines. And they're called, their names are adenine, which can bind to thymine, and guanine, which can bind to cytosine. And the binding goes AT and CG, and so if one of the, if you have a chain of single-stranded DNA that's AACC, then it will be mated with another chain of single-stranded DNA, which will be TTGG. And so this carries the code. The code is a 3 nucleotide code. If you have 3 bases, that will tell you what the appropriate amino acid is. Yeah, everybody's class dismissed. I'll go on for another few minutes. If those of you want to hear a little bit of molecular biology, can hang around. Have a nice summer, everybody. Please do the quizzes by noon on Thursday of next week. And if you want to learn something about imaging in molecular biology, come at 3:30 to this room on next Thursday. Thank you. And if you haven't signed in, the sheet is somewhere in the front here. All right, here comes John. I'll just
Have
stop.
you done the final quiz?
I'm most of the way through.
You didn't ask me to do the calculus thing.
Oh, shoot. I forgot about that.
But it's not too bad.
Yeah, I can't give part of my lecture because there was no computer.
It's basically just finished on your
Is it just like general physics stuff?
In general physics, we went over everything that's on the quiz, except we just talked about it, and now you actually have to apply it. So
Yeah.
it might be. Oh, yeah, Nancy. You too.